It's like you're studying. Like, are you serious? I told her, I was like, I asked her. So
Okay, if you can turn to page 5 in your test review packet. So up here on the board, these are the problems that I'll be checking for completion on Wednesday. When you guys take your test, I'll be collecting your test review packets. So if you've been absent 1 or 2 days, just make sure you can go through and circle the problems that you're going to want to finish for Wednesday. So we've done page 1, page 3, select problems from page 2, 3, and 4. And then on Friday, we did page 4, number 6, and then all of page 15 and 16. Okay. Today, we're going to work on all of page 5. And we'll focus our attention, continue to focus our attention on curve sketching. So we'll do a couple of curve sketching problems today. Tomorrow, we'll finish the packets. And I have a related rates worksheet that will look a lot like what your test problem will look like. So we can kind of have a mock test environment for this problem to see if you can try it without any help. Of course, you can use your calculator and see how your steps look, and then we can compare our answers. And then on Wednesday, I will have a morning help session at 7:15. And tomorrow, I'll give you a separate morning test review worksheet for you to try either at home Tuesday night or wait for me to go over with you on Wednesday. And just to revisit, if you can turn to page 30 again, what we're working towards here. So inverse trig derivatives, being able to apply the rules for those types of problems. Implicit differentiation involving trig, we'll see that today as well. Particle motion problem. We've done that before. We're just finding velocity or acceleration or evaluating velocity, evaluating acceleration. Related rates, we've been working on that. Mean value theorem. We can revisit that today or tomorrow. And then focusing on trig curve sketching problems a bit more today as well. And then we can also practice our derivative rules today at the end of class today as well. All right, page 5, worksheet 3. Right, so here's the diagram that should have been given to you. You just go ahead and draw that in. Suppose the bird is flying horizontally 40 feet above your head at 20 feet per second. So the fact that the bird is flying horizontally, that's going to cause that height to never change. It's going to hold at 40 feet. But x is going to change. As the bird gets further and further away, that x is going to increase. And then we can expect that theta to also change as well. How fast is the angle of elevation changing when your horizontal distance from the bird is 30 feet? So we can use that 30 feet later on after we find the derivative, we're trying to create that second triangle to find the ratio. So go ahead and see how far you can get with this problem. Build your trig equation, find the derivative. The theta dt will show up, the x dt will show up. See how much you can fill in. See if you can build your second triangle to replace your trig function. See how much we remember. I'll go through steps with you. All right, so we start off with tangents, right? Tangent allows us to target that theta along with 40 and the x. The nice thing about that right side is there's a constant that shows, which means we can avoid quotient rule. We can just move things around and just rely on power rule to get through our derivative process. All right, derivative, tangent becomes secant squared, d theta dt. Power rule. Let's do some cleanup here. All right, so let's see what information the problem provides for us here. 20 feet per second flying away from the viewer here. So we know dx dt is going to be the speed that the bird is flying. How fast is the angle of elevation changing? We know we're looking for d theta dt. At the moment when the bird is 30 feet, so 30 feet away from the person standing here. So that's going to be this moment in time, x is 30. All right, so if we look at what information we can plug in, we can replace dx dt with 20. We can replace x with 30. We know we're looking for d theta dt. So then the last piece of this puzzle is trying to find a replacement for secant of theta. So we're going to draw a second triangle. Fill in the values at this moment in time, 30, 40, and the Pythagorean theorem, which will give us 50. All right, so secant of theta. We know secant is related to cosine. Cosine is adjacent over hypotenuse. So therefore, secant must be hypotenuse over adjacent. I'm going to just reduce it to 5/3. Put that information in. Secant needs to be squared. So 5/3 squared. dx dt, which is 20. Okay. We know that 5/3 squared is 25 over 9. Flip that over to the other side, becomes 9 over 25. And the rest can just go in our calculator to find a numeric value that represents d theta dt. Okay, any questions with number one? All right, take a look at number two. We have to rely on a couple of different rules here. E to the u, sine of u, and natural log of u. And also the x times e to the sine of 2y, that's an indication that we have to go through the product rule there, two different expressions being multiplied. And then you also see y's mixed into the equation. We know there's also implicit going on here. All right, so try number two. I'll work through the problem as well. The rule for e to the u is e to the u times u prime. Sine of 2y becomes cosine of 2y times u prime. 2y's derivative is 2 dy dx. Okay, 4x becomes 4. Natural log of y becomes, the rule for natural log of u is u prime over u. So 1 over y and dy dx. Okay, we have two y variables to begin our equation. So we should be expecting 2 dy dx's in our derivative step. Okay, we're done with the calculus. Now you're just moving things around, trying to collect your dy dx terms together so that you can factor that out. So I'm going to see if I can compress some of these terms together first. Dy dx. All right, so I have two terms that I want to put together on the same side. So we move them together onto the same side. Okay, factor the dy dx out. Okay, divide all that over. I think on my key, I try to collapse the complex fraction, but you don't have to. As long as you have the dy dx by itself, that's good enough. Okay, any questions? Okay, number 3. Find the equation of tangent lines. We have to find the derivative. From the derivative, plug in the x value to get the slope, and then do point slope form. Okay, does anybody still need to look at number 2? And we definitely need to remember our arc cosine x squared rule. If we think about the 2 columns of derivative rules for arc trig, we know that all the c functions for arc trig are just the variations, the negative versions of the ones to the left of them. And arc cosine is related to arc sine. And then careful, this is not just arc cosine by itself. We can't jump into this rule and just treat that alone. There's an x in front of it. These are 2 separate terms. We got to go through a product rule as well. Negative u prime over square root minus u squared. My u value is x squared. One minus u squared, x squared squared. So that's x to the fourth. Okay, so really the only thing we need from this is finding the slope. So I know that my x value is 0. So if I find f prime of 0, I can work towards finding my slope, which I can use for my tangent line equation. Now, we can't just leave it as r cosine of 0. We have to get it down to a numeric value. So r cosine of 0 is same thing as saying, well, what theta value will allow cosine to be 0? That's what it's asking. And we know cosine is equal to 0 at pi over 2 and 3 pi over 2. Sorry, domain is from 0. Oh, they tell us domain is from 0 to pi. And so because of that, we can remove that 3 pi over 2, just pi over 2. So therefore, my f prime of 0 is just pi over 2 minus 0, which is pi over 2. Okay, we have everything that we need. We have our order pair, we have our slope. Okay, number 4, arc trig is involved, implicit is involved, and then we're going to have to, after we gather our dy dx, we'll plug in the order pair to get the slope, and then same thing, point slope form. Find number 4. A couple of things to keep in mind for number 4. There's implicit going on, multiple y's mixed into the equation. And then we also have to recall our rule for arc tangent. Now, careful here. This whole x plus y is our u value. We cannot distribute the arctangent through, right? We can do that if for some reason that arctangent was outside of the x plus y, but that x plus y is inside the arctangent, so we can't distribute. We have to just leave it in the way that it gives us, and That whole parentheses is our u value. I worked it out a different way on the key, but we'll just apply the rule here. Since my u value is x plus y, the derivative of x plus y is 1 plus dy dx, all over 1 plus u squared. I need to square this entire x plus y squared. We have two different y variables, so we should be expecting two dy dx's to pop up in our derivative. Y squared becomes 2y dy dx, power over 4 goes to 0. Now, this is a little messy here, but we're not having to worry about finding the derivative equation. We just need to find the slope. So we can save a little bit of time rather than spending the time rearranging. Let's just go ahead and plug in our ordered pair 1, 0, and then a lot of the terms will just clean up nicely for us, and we can just solve for dy dx from there. So I'm just replacing every x and y with 1 and 0, and then solving for dy dx. So the whole right side will just wipe away because everything is times 0. The dy dx goes away here as well. I'm just left with 1 plus dy dx on the left side over 2 equals 0. If I cross multiply, I'll get, if I think of it as 0 for 1, cross multiply 1 plus dy dx equals 0. Solve for dy dx. I get -1. Or we can multiply both sides by 2 and then set that equal to 0. Either way, we should get a slope of -1. Okay, we have our ordered pair, we have our slope, point slope form. Okay, next page. Let's go to page 6. Let's do a full curve sketch problem. Okay, so we find the derivative, set the derivative equal to 0, find our critical points, populate our f prime sign line, fill in our intervals of increase, decrease, and then repeat that same process for the second derivative function, second derivative sign line. Let's do inverse cosine here. So we can isolate the 2x, move that cosine over, make it inverse cosine. This is basically asking, okay, where is cosine equal to 0? Cosine is equal to 0 at pi over 2, 3 pi over 2. I'm sorry. Wait, cosine. Yeah, that's right. Just to be safe, I'm going to go a little further out than my initial 0 to 2 pi because I'm going to divide by 2. It's going to end up shrinking the value. So I'm going to find some more coterminal angles so that after all these values shrink, I can make sure that I'm not accidentally missing out on additional critical points. So if I were to find additional coterminal angles, if I add 2 pi to pi over 2, I get 5 pi over 2. If I add 2 pi to 3 pi over 2, I get 7 pi over 2. Okay. Now, divide everything by 2, or same thing, multiply by 1/2. So you see how all these values shrink to between 0 and 2 pi, but our interval is only from 0 to pi, so it ends up working out where we don't need these values. But I think it's always a good habit to build out more than we think we need, especially if we're going to end up shrinking those values by sometimes by 2 or 3 or 4. But yeah, right now, these are outside the intervals that we need. Okay, we test each values in each subinterval with our derivative to gather information about the slope behavior. So here I'll choose pi over 6. Here I'll choose pi over 2. Here I'll choose 5 pi over 6. Okay, so plug pi over 6 in for x. I'm going to end up with cosine of pi over 3. We know cosine in the first quadrant is always positive, so plug pi over 2 in for x of my derivative. 2 times pi over 2 is pi. Cosine of pi is -1. 5 pi over 6. 5 pi over 6 in for x, I get 10 pi over 6. 10 pi over 6, same thing as 5 pi over 4. Sorry, 5 pi over 3, which is in the fourth quadrant. So positive value. Okay, so we have a relative maximum at pi over 4, a relative minimum at 3 pi over 4. We have two intervals of increase, one interval of decrease. We can find those order pairs by plugging these x values back into the original function. So we get sine of 3 pi over 2, which is -1. Relative max. Pi over 4, and for x, 2 times pi over 4 is pi over 2, sine of pi over 2 is 1. Okay, let's go ahead and gather information from the f double prime sign line, or for f double prime first. So we know if our derivative is 2 cosine of 2x, the derivative of cosine of u is negative sine of u times u prime. Set that equal to 0. Divide both sides by -4, get that to go away. Inverse trig, let's get that 2x by itself. So inverse sine of 0, where is sine equal to 0? Sine is equal to 0 at 0, pi, 2 pi, 3 pi. Okay, I'm listing more than I need here. Dividing by 2, same thing as multiplying by 1/2. Okay, I don't need the 3 pi over 2, 4 pi over 2. I'm only looking at what's between 0 and pi, since that's our interval here. And 0 and pi are endpoints. It's really only pi over 2 that's going to show up in between our interval here, in between our bounds. So pi over 4 lands between 0 and pi over 2. I can choose any number of values here. Pi over 6, I can choose. All right, you have a number of options here. Anyways, we know that sine of pi over 4, that gives us plug in 2 multiplied by 2 here. That's really sine of pi over 2. Sine of pi over 2 is going to be +1, but 1 times -4 is negative. So second derivative function here. So we're talking about concavity here. 5 pi over 6. It's really the same thing as 5 pi over 3. 5 pi over 3 is in the fourth quadrant. Sine in the fourth quadrant is going to be negative. Negative times negative is positive. So We do have 1 point of inflection at pi over 2 because there's a change in signs. Plug pi over 2 back into the original function because we're looking for a physical location on our graph. Sine of 2 times pi over 2 is going to be pi. Sine of pi is 0. So point of inflection at pi over 2 comma 0. I think we should have enough information to sketch our graph. Let's go ahead and also find the endpoints. Since we want to know where our graph begins and ends, we have our most important points, though. We have relative min, relative max, POI. If I plug 0 in for sine of 2x, sine of 2 times 0 is 0, sine of 0 is 0. And then f of pi, I guess sine of 2 pi, that's also 0. So we're going to start and end at 0. We should be able to get a pretty good sketch of our curve. Okay, so border pair 0, 0, pi comma 0, pi over 2 is also at 0, pi over 4 is at positive 1. Relative min, 3 power 4 is at negative 1. So we kind of already know how the graph's going to look. But if we just look at our slope sine line, we know our graph is rising, falls, and then rises again. Now that we have the path of our graph, we can give it the curvature that it needs. So between 0 and pi over 2, our graph is going to have a concave down shape and then shifts back to concave up the rest of the way.
Yeah.
Okay, page 17 and 18 are just additional related rates problems. We can pick those up tomorrow, but I do have one more thing that I want us to do, and that is with our rules. So if you can turn, there's a couple of blank pages in the back of your packet. This is page 28B. So let's practice our derivative rules again. Let me And again, there are actually 3 more rules that we need to know, but I'm leaving those out. Those are arc cosine of u, arc cotangent of u, and arc cosecant of u. And those are just the negative versions of these unique ones. All right, check your derivative rules. Tomorrow we'll have one more day of test review. Test is Wednesday, morning health session, Wednesday morning. All right, come to your phones.